Hi guys, welcome to Biophysics class 28. This is Micelles versus planar bilayers, segment 2. And in this class, we're going to look more carefully at the curvature of the planar bilayers and generate a model for the curvature of a cylindrical bilayer. So let's review. Last time we looked at Micelles versus planar bilayers. And in the planar bilayer, we have, in general, well, in the pure plane, we have two straight um, segments with hydrophilic heads and hydrophobic tails. And we discovered that the planar bilayer can accommodate double tails more easily than can a micelle. But recall that the edges of the planar bilayers expose some of the hydrophobic tails. So if we just have a straight linear planar bilayer, we have an energy penalty from this from these exposed hydrophobic tails exposed to the aqueous solution of the cell. So curving the planar bilayer, as in this effect here, where we've taken this and sort of wrapped it around with the one of the layers wrapping around to be the inner circle and the other layer wrapping around to be the outer circle here, keeps these tails from being exposed because of the nature of the cyclical nature of the circular pattern. So that lowers the energy E and also lowers more importantly, the free energy E minus TS. However, curving the bilayer also stretches the heads of the amphiphiles from their optimal area as a head. So in the purely planar bilayer, the amphiphiles are in their, the amphiphile molecule, the head molecules structures are in their lowest free energy configuration. But when we stretch or when we curve them into a circle, they're going to stretch a little on the outside and become A head plus some delta A. And they'll also contract a little on the inside and become, that's not shown here, and become A head minus delta A. And that, since they're different from their optimal area, that's going to raise the free energy by raising the energy. Still, the net effect almost always is to favor curving the bilayers. So in cells, we usually almost always find curved bilayers, and we'll find out what type of curved bilayers are most common in the cell in the course of this lecture and in the exercise you'll do in the class. So how about a model for the free energy cost due to stretching these heads? Okay, well, here's our free energy, here's our amphiphilic double bilayer, and here is a one of the heads, the hydrophilic heads, and it's being stretched from its optimal length A head to A head plus delta A. Okay, and similarly, it's not shown here, but the inside would have been contracted to A head minus delta A. So we can say that the change in the free energy can be expanded as a series in delta A squared and delta A cubed. But the coefficient of the linear term, delta A, must be 0, or else we could bend, or else by bending, we could lower the surface free energy, okay? Because if C1 were, say, positive, then by making delta A negative, that is the inner surface here would have a delta A negative, that would lower the free energy. So this linear term must be 0. And then this cubic term, we're assuming this delta A is fairly small compared to the area of the head. So this cubic term is going to be, delta A cubed is going to be a small number compared to delta A squared. So the linear term and the cubic term and further terms would drop out. And so we just get that the change in the free energy would just be the squared term, C2 times delta A squared, which we rewrite in a more familiar form as 1/2 K times delta A squared, since we're used to seeing like 1/2 KX squared for the mass on a spring or the harmonic oscillator. Okay, so so what can we do next? Well, if we think about the expressing this delta A a little more closely in terms of the geometry, we see that this outer layer has, in this depiction, has a radius r, and the chain d is the length of the hydrophobic tail. Okay, and so when this is curved in along one direction, okay, so this curvature only occurs along one direction of these circles. Only this the direction of along the circumference of these cylinders is getting lengthened. The direction perpendicular here is not getting lengthened. So we can say that for this cylindrical bending, the ratio of delta A over A head is just going to be equal to the ratio of delta R over R, because this dimension, again, this perpendicular dimension stays the same. So the ratio of delta A over A head is the same as the ratio of this change in this length over its initial length, which is this by similar triangles, the same as the change in the same as the difference in the length to the entire length, which is delta R over R, delta R over the initial length, which is R. And then delta R here would be D. So we can say that the ratio of delta A over the A head is equal to D, the length of the hydrophobic tail, over R, the radius of the outer part of the bilayer. So rearranging that, we get that delta A is equal to A head times D over R, just multiplying through by A head. And then substituting that into this expression here, we find that the change in free energy per head, this is change in free energy, this is for a single head, is equal to 1/2 K times delta A squared. So I've just substituted in this A head D over R, capital R squared here, okay? Okay, but what we're really interested in is not necessarily per head, but the change in free energy per area, because that determines the surface tension and determines the shape that will actually be assumed by the planar bilayer. So the change in free energy per area can be written as the change in free energy per head, which we just calculated, times the number of heads per area. Well, I've just substituted back in the change in free energy per head. The number of heads per area will be 2, because each area here has an inner head and an outer head, and they both have a linear change delta, well, plus A and minus delta A, but in the change in free energy, delta A is squared, so it doesn't matter if it's positive or negative. So it would be 2 two of these heads over the area, which is A head. And so if we multiply everything together, these twos cancel. We get a K times A head squared over A head, which is A head, and then times D squared over R squared. Okay? So we get this term here. So that's the change in free energy per area. And often this is just written more simply by defining kappa as 2 times K times A head times D squared. So 2 times K times A head times D squared. And with kappa defined in this way, the change in free energy per area is 1/2 kappa times 1 over R squared. Okay, so you can convince yourself of that. If you plug in kappa, the twos cancel. We just get K A head D squared over R squared like we had up here before. All right, so what does this mean? This is for cylindrical bending. Well, for a cylinder, the area, the surface area of the outside of the cylinder, so if this cylinder extended outward, is proportional to R, because the area of a cylinder is 2 pi R times the length of the cylinder. But it's proportional to R, so because of that, if we multiply, that is the surface area of the cylinder being proportional to R, we multiply by the area, so to get the change in free energy, we're going to be multiplying by R, 1 power of R. That means the change in free energy will be proportional to 1 over R. This means that if the change in free energy is proportional to 1 over R, then the smaller R gets, that is, the smaller the tighter this planar bilayer is wrapped, the smaller the radius, the larger the free energy penalty. Okay, so we can't make very small and long cylinders that these will the free energy penalty from wrapping them so tightly and stretching their areas will probably not compensate for the free energy loss due to hiding their hydrophobic, hiding the hydrophobic tails from the planar bilayer. Okay, so larger radius cylinders could be possible, but in the in-class, we'll look at the question, what about spheres? Okay, so you can think we'll be doing an exercise, a similar exercise to this, but in the case of spheres. So you may want to ponder what would change in this analysis for spheres before class, but as I say, in class, we'll do that exercise for spheres. Okay, so in summary, we've looked and we've seen that planar bilayers will tend to bend to reduce the overall free energy, and we have a working model for the bending for a cylinder, and we found that small radius cylinders would be very unlikely to occur because of the large range in free energy. All right, great. Thanks for your attention, and I'll see you in class.